Redner on evolving complex networks.
Okay, thank you. So this lecture is going to be rather different in style than the other three because in this particular lecture there is a reasonable component of my own work in this, and so it's more modern, I would say. But what I want to try and do is present some what I would consider classic textbook information that you should know about the evolution of complex networks. So I'm going to begin with an old golden oldie, the so-called Erdos-Renyi random graph. And if you don't know what that is, don't worry about it because I'll define it. Then I would go to the next problem, the so-called random recursive tree. And the random recursive tree is actually older than Erdos-Renyi random graph. This was introduced in 1959. This is introduced like in probably the 1800s. I have to admit I don't know where it started. But as you're going to see, there's a very natural segue between the random recursive tree and the so-called preferential attachment networks, which have been very hot in the past decade. In fact, the ideas underlying the preferential attachment network have been around for 80 years, and it's just that it's only in the past 10 years that people have really appreciated what they were doing. So I'll describe to you basically how you can apply the master equation approach to understand a lot of the basic phenomenology of so-called scale-free networks. Okay, so let's start with the Erdos-Renyi random graph. So the model is amazingly simple. It's as simple can be, and it's astounding at how rich the phenomenology is in this model. So here's the way the model starts. You begin with n isolated nodes, and if you imagine that every node potentially could be connected to anybody else, then there would be n times n minus 1 over 2 possible pairs. And the limit of large n, I'm going to forget about the minus 1, so it was roughly n squared over 2 pairs. And the basic idea of the Erdos-Renyi random graph is that you then start randomly populating the links between any pair of nodes with equal probability. And so here's like a little cartoon of the thing starting. I just add nodes at some constant rate. So that's all that's happening. I just take any two nodes and I add a bond and I get to some point. So the thing is that in the original development of Erdos-Renyi, this was treated as a purely equilibrium problem. That is, you would look at a snapshot of the network at this stage, and then you would study like the cluster size distribution or various geometrical features. There was a very nice insight by Ben Naim and Kapinski, which is instead of looking at this graph statically, look at it dynamically, as you saw in this little animation. And if you then develop a kinetic picture of this, many of the interesting phase transition properties and geometrical properties that took Erdos and Renyi, very high-level mathematics to understand, can be understood in a very simple and natural way by the master equation approach. So the one other feature here is that it is convenient to choose the rate at which you introduce links to be n over 2. So each time step you add n over 2 links into the problem. And then if you count the total number of links at time t, so it's time times n, it's the time t times n over 2, so you get nt over 2. Now the thing is that the average degree of a node, and degree is defined as the number of links attached to a node. So let me just draw a little picture. Here's a node. Here is a bunch of links. So this has degree equals pi. And the point is that the average degree averaged over all nodes of the network is precisely twice the number of links divided by n. And why the factor 2 here is just the fact that every single bond here which connects and contributes to the degree of the node, this bond also connects to another node. And so each link is counted twice. So the average degree is 2L over n. And using this rate, then one gets that the average degree is exactly t. So it's a convenient parameterization because every time step, the average degree is increasing by 1. So we are now going to be thinking about a stochastic process where the average degree of each node increases by 1 at a unit rate.
So it's the same as coordination number?
Yes. Yeah, degree is the same as coordination number. Yeah, so like I'd say the coordination number is the equilibrium stack mech way of saying degree, and now degree is kind of the graph theorist way of calling coordination number. So let's now study the degree distribution. And probably some of you have heard that the degree distribution is the thing that was the focus of much attention in the early work of Barabasi-Albert. Let's first study it for the simple Erdos-Renyi random graph. So there's two versions of the degree distribution we can study. We can study the total number of nodes of degree k, or the fraction of nodes of degree k. And as I hope you'll see momentarily, it's much easier to work with a fraction of nodes rather than the total number of nodes, an intensive quantity rather than an extensive quantity. So here's the master equation for the fraction of nodes of degree k. So since the degree is increasing by 1 at rate 1, then the rate of change in the fraction of nodes of degree k, so there is a gain term because every node of degree k minus 1 with rate 1 will be converted to a node of degree k. And any node of degree k at rate 1 will disappear because it becomes a node of degree k plus 1. So this is the master equation that describes the evolution of normalized degree distribution. And again, just repeating what I said, the black corresponds to the gain term, and the red corresponds to the loss term. And so hopefully you recognize this differential equation because it's nothing more than the differential equation that defines the Poisson process. And so you can just start, say, with a delta function distribution that every node has degree 0, and then you find that this is a solution. So it has a Poisson degree distribution. So Jordan, yes.
Is the average number of nodes you find one realization of reading this graph, or?
Correct. Well, as opposed to what?
Well, I would imagine that every time I wrote this graph, my distribution of degrees would be different.
Correct, absolutely.
So what would the average?
Yeah, so, okay, very good point. I mean, probably what I should have written here is I should have included the word average over a large graph. In fact, you can actually develop this master equation approach to find the distribution of the degrees, but that's a whole other talk. It's horrible mathematics. It's not of any physical interest. Anyway, so the upshot of this little story is that the degree distribution is Poissonian, so it means that it doesn't have a broad tail. It's a relatively sharply peaked with a mean degree which grows linearly with t, and a fluctuation or dispersion of degree which scales as root square root of t, so the average, the relative fluctuation is scaling like 1 over the square root of time. So that is the degree distribution. The other feature about the Erdo-Schrödinger random graph, and the one that probably was the original motivation for it, was to understand the percolation transition. So perhaps some of you are aware of the classic lattice percolation process, where you take a lattice of sites and you randomly occupy the bonds between nearest neighbor sites. And as you increase the density of bonds, one undergoes a percolation transition where one has isolated small clusters of bonds to a globally connected cluster that spans the system. And so that happens at a percolation transition. So similarly here in the Erdo-Schrödinger random graph, there is a similar percolation transition. And the nice thing about it is that one can understand all of its features while using this master equation approach. So let's first of all look at this system. And if you just, what I've done here is I've counted the cluster size distribution. So we have 4 isolated sites. So there's 4 clusters of size 1. There's 1 dimer, so 1 cluster. I'm sorry, there must be another one somewhere. Yes, there's another one here. So there's 2 clusters of size 2 and 1 larger cluster of size 6. And let's now ask how this cluster size distribution evolves as I add more bonds to the network. And the basic point is that as you add links, all that can happen is clusters merge. We started with n clusters, isolated sites, and we're just joining them together. So the number of clusters is decreasing with time, and we want to understand how that happens. So let's now focus attention on 2 different clusters, the green guy and the purple guy. And we can ask, what is the rate at which these 2 clusters will merge? So here I have a cluster of mass I. Here's a cluster of mass j. And if I find, if a bond was added here, then these 2 clusters will merge. And what is the rate that will occur? So clearly, since any bond can link, it can start at any site of the network and go to any other site of the network, the probability of having one end of the bond on this cluster is proportional to I. The probability that the other end of the bond touches the other cluster is proportional to j. And so the merging rate is exactly equal to ij. And that's exactly what I was talking about in my first lecture, product kernel aggregation. So that's what's nice about this kinetic feature is that we can think about these cluster concentrations CK, and the equation of motion for them is precisely that of product kernel aggregation, which I discussed on Monday. So we can then apply all the technology that we learned from master equation approach to essentially understand the percolation transition. And so we know what the solution for the cluster mass distribution is, or the cluster size distribution. It's this weird, very simple but weird function that has these different behaviors. That at t equals 1, there's a power law distribution of cluster sizes, and that corresponds to the emergence of an infinite cluster. And for t less than 1, there's an exponentially decaying distribution, which means that your largest clusters in a finite network of n total sites will be of the order of log n in size. Whereas at the percolation transition for a finite network, the largest cluster will be of the order of n to the 2/3 in size. And exercise for the students. I've just now pulled something over your eyes that said the largest cluster was of order log n over here and order n to the 2/3. How do you derive that? So I leave that as an exercise for the student. Okay. And as we saw for Monday, the average cluster size, which is naturally measured by the second moment of the cluster size distribution, diverges at t equals 1. So once we reach t equals 1, there's one giant cluster, and eventually, as time goes on, this giant cluster sucks up everything else. What's really cute about the Redirection random graph, which is not contained in the lattice percolation process, is that this sucking up of all clusters becomes a complete process at a time which is of order log n. I'm sorry. The time is log n. When the time is log n, then in fact there's no finite clusters left at all. Everything is just stuck in one infinite cluster. So it's very different than good old lattice percolation.
Excuse me.
Yes?
Let's go back to the slide.
Just have to... Yeah, go ahead, ask your question.
Yeah. So for the two results for t smaller than 1 and t equal to 1, can you prove for the first result, if you take the limit t approaches 1, can you prove the two results are subconsistent?
Absolutely. Yeah. I mean, the thing is that I think I wrote it down in the blackboard, on Monday. But the thing is that as t approaches 1, this has a power series extension, so it's basically t minus 1 squared over 2. And so when t goes to 1, this just all goes away. I mean, the thing is, this is actually a bit sloppy because the point is that in front there's a prefactor, which I should have written, but I didn't write. So there's the same 2 pi to the minus 1 half k to the minus 5 halves times this exponential. Okay. So it's my mistake. I should have written that there. Yes?
When you say infinite cluster, you mean something is proportional to n?
So if the first point is that normally one deals with the Redirection random graph when it has a finite number of nodes. Mm-hmm. So when n is finite, then below PC the largest cluster is ordered log n. At PC or t or critical time, the largest cluster is of order n to the 2/3 in size, and above t equals 1 or above PC, the largest cluster is order n. And remember, there was that equation I wrote last time that the gel fraction was g times 1 minus e to the minus gt, the solution of that transcendental equation. So that's the gel fraction. So the size of the largest cluster is g times n. Okay. So now let me go on to the next model I'd like to present, which is the so-called random recursive tree. And as I said, I don't know who thought it at first, but the notion of looking at random trees in general was first done by Cayley in 1857, so this is an old field, and Paul in 1937. And this paper by Otter, he actually counted the total number of trees of a given size, random recursive trees of a given size. So it seems that maybe this is the first paper that specifically deals with so-called random recursive trees. So what is a random recursive tree? And so let me now make a cartoon that shows you how you do it. So you begin with a single site, so here's site 1. And then you add nodes to the network one at a time. So here's a few nodes being added. But the crucial point here is that the rule for adding is that you attach to any earlier node randomly and uniformly. So you don't pay attention to anything about the structure of the nodes. You just say, at this stage of the game, I have 5 nodes, and I'm going to pick node 5 with probability 1/5, this with a 5th probability, all the nodes with a 5th probability, and then I just attach randomly. So here we go, we just add a few more nodes, and so you get some kind of structure, whatever it happens to be. And I'd like to now analyze the structure of this random recursive tree. So the basic observable that I want to focus on, and also was the focus of so much attention in all the scale-free networks, the Bar-Bossi, the Albert model, and so on, is this degree distribution, which is what is the number of nodes of a given degree. So here we have a node of degree 3, here's another one of degree 3, here's one of degree 2, here's one of degree 1, and we just want to count the full degree distribution. So this is the quantity that I'd like to solve for. And once again, the master equation approach provides a very natural and simple way to get this with very little computational labor. And as you're going to see, the master equation for this model is almost the same as the Erdos-Redier random graph. So I'm only proceeding in tiny little baby steps. Like once we've derived one equation, the next one follows just with one little extra twist to it. So here's the master equation for the random recursive tree. And let me remind you what we had before for the Erdos-Redier random graph. So this looks similar, but it's not quite similar. And let me focus attention on the differences, because they're really not very serious differences. The first point is that in the Erdos-Redier random graph, I had a time variable that I defined by setting the rate at which links were added to the network. And in this case, I'm using as my time variable the total number of nodes that I'm adding to the network. So in some sense, there's no notion of time. Every time I add a new node, my basic time-like variable increases by 1. So my time variable is just the number of nodes in the network. So that's to replace t by n. The other thing is that the two black and red terms are just as before. And the only other really fundamental new feature is that I have a delta function here because every time I add a new node to the network, the tail end of the arrow is in the source of a new node, which necessarily has degree 1. So at every step of the process, there's a change in the degree distribution because of who I attach to, but I'm also creating one node of degree 1 every time I add a new node. And finally, the denominator factor n is that because I was dealing with this extensive quantity, the total number of nodes, and I divide by n to get like the fraction of nodes of a given size. And so that's the master equation for the for the random recursive tree. And again, just look at how similar it is to that from the Erdos-Redier random graph. So let's solve this equation. And in fact, there's really nothing to it. If you just, for exercise, again, I leave this for you to do because it's really quite simple. Just solve these equations one by one. So you write the equation for n0 by dn. So there's no gain term. So you have n0 dot is minus n0 over n. And there's no delta function. So that's the easiest way to solve. And just do it one by one. And what you'll find is this very suggestive looking solution. Another way you can do this is that you notice that forgetting about the number of nodes of degree 0, which are disappearing, that these guys are all proportional to capital N. So if you make the ansatz of capital NK, the number of nodes of degree k, is proportional to the total number of nodes of the network times the normalized density. If you substitute that above and just divide out the n, then you get a much simpler recursion formula. And so this recursion formula, you don't even have to be a university student to do this. This is what you learn in high school, and then you can solve that one directly. Yes?
Yeah, so what about loops?
So loops is a completely different matter. If you want to do loops, that's a little bit harder. And I'm not going to discuss this here because I'm only dealing with the random recursive tree. So one thing I will say is that if you allow, for example, a new node to join to several nodes at once, 7 or 10 nodes or 3 nodes, then you can develop closed loops. In terms of the degree distribution, my belief is that it does not affect the degree distribution. And in fact, in the case of the Barabasi-Albert type models with out degree larger than 1, we can apply this master equation approach, get the degree distribution, and find that it agrees extremely well with simulation results. But we can't prove that it's exactly correct. But on the other hand, the topological features of a network with loops are completely different. And so there's some other features of the network that this master equation approach has not yet been able to resolve some elements of the network. Anyways, so the solution for this one is really simple, and it's kind of as you might have expected. The degree distribution is still fairly sharp. It's an exponential distribution. The number of nodes of degree k is 2 to the minus k. So now I want to turn to an area where this is where I come into the game, which is that with Paul Krupitsky, we study various modifications of this uniform attachment or this random recursive tree. And this is one of those things that it's not easy to explain, like how this came out of the blue, but if I remember correctly, there was a paper by Kleinberg and company, who are computer scientists, who were somehow vaguely thinking about this notion of that you might attach here, and then you say, oh no, I want to attach there. And so it was in the air somehow, this notion of redirection. And it turns out that if you augment the random recursive tree by redirection, something magical happens, and you actually understand everything about the scale-free networks almost complete. So let me define now the notion of redirection, because it's a very simple construction, and I think it's actually quite powerful in its implications, and I think I'd like to sort of advocate this, that sometimes it's useful to twist a problem around in a way that you don't expect, because some nice stuff can happen. So let's now think about one step of addition in the random recursive tree. So here's a new node. And what the new node does, according to the random recursive tree algorithm, is that it picks a node at random. So it picks a random target, and it attaches to it. And in this model of redirection, what I'm going to say is that instead of attaching to a random target for sure, I'm going to attach with the probability 1 minus r, where r is less than 1. So if I don't happen to attach, what I'm going to do then is that I will jump to the ancestor of this random target. So with probability r, I'll attach to the ancestor. So again, I pick a random target. With probability 1 minus r, I'm happy with who I attach to it. I just attach to it. And with the probability r, I go to the father of this node. So this seems very innocuous in that it shouldn't make much of a change. But in fact, there is a very important, I don't know what to call it, geometrical feature of the network, that the average degree of the ancestor is very different than the degree of a random target you can pick. So again, I think I might have mentioned this in a comment I made earlier in the week, that if I pick somebody random and ask, how many friends do you have? So say you have 5 friends, and I say, pick one of your friends. And then I ask, how many friends does your friend have? On average, it will be higher than the average number. And the way that one can see this in the framework of this picture is that what is the rate at which you attach to an ancestor node? In order to attach to this node, I first have to attach to an upstream neighbor and then do the redirection. So the rate at which you attach to any particular node is proportional to the number of its upstream neighbors. So the more upstream neighbors you have, the more likely you'll attach. So the rate at which you attach to an ancestor node is now going to have a dependence on the degree of that node. So an ancestor node that's got lots of upstream neighbors is more likely to be attached to by this redirection mechanism than a node that doesn't have a lot of upstream neighbors. And so this is an implied linear preferential attachment that comes out of a purely local rule. And so this is another important aspect of this model, which if any of you are simulating complex networks, I highly recommend this, because in this algorithm, as you're going to see, produces linear preferential attachment. But the thing is that this model involves only local information. Just to attach to a node at random, and then I go to an ancestor node. It's an order 1 number of computer steps to derive it. And so in the early days when we were doing this, I guess I wasn't very good at publicizing it. And so people were simulating, the scale-free networks of 10 to the 4th nodes, and it was considered a big deal. But for this, I could easily simulate 1 billion nodes with no problem, and so I mean, it's 4 orders of magnitude faster than the standard way of doing the simulation.
So you attach probably 1 minus r to some node.
Right.
And then you detach from that node to
Yeah, so the thing is that this you should view as like a provisional attachment. So you begin here and you say, here's my target node. And I just say, provisionally I'll attach it with probability 1 minus r. With probability r, I attach to his father. And that's it.
Independent of what r is.
Well, no, r is going to be the one parameter in the model. So I fix r, and you'll see in a minute what is the meaning of r. But let's just fix r at 0.1, for example. So when I pick a node at random, 90% of the time I'll attach to the node itself. 10% of the time I'll go to its ancestor. And r is fixed throughout the entire process.
So you don't attach to both?
No, it's only attached. I'm only going to here. So what I should have done maybe in animating this is have this arrow disappear and I attach the ancestor. Yes?
And how do you define the father node? It's the one that this node points to?
That's right, because see, since in this model I have only one outgoing arrow, everybody has a unique father.
What do you always have an arrow that points? I mean, can you have all the arrows that will be?
Well, the thing is that every node has only one unique father. If I have out degree larger than 1, then there's some ambiguity. Who is your father? And in fact, Danny Ben Abraham, who's speaking next week, actually generalized our approach to multiple fathers, and so he has a way of like doing the same redirection game for much more general networks and gets useful results.
You always have an arrow going up.
Yes. Oh, okay. So in fact, maybe you pointed out something a little bit dicey here, which is what happens if I attach to this node? It doesn't have any father.
Yeah.
So in order to avoid that, so it's a small technical glitch, which is that what you do is you start with you've got to have a suitable initial condition. So for example, you could do an initial condition like this, that this guy is pointing this way, that guy's pointing that way. Now every node has a father, even though it goes around in a closed loop, and then you just build from this network. Or you could do even something simpler, although it has like, it has now one node which has, well, okay, that's fine. So and that's how you can do it.
Can you just do a self loop?
Yeah, you can do self loop too. Anything, so as long as every node has a unique father. Was there other question?
Are you going to tell us what linear preferential attachment is? Or?
Yes, I'm coming to that in a moment. Okay, so anyways, the point is that because the attachment rate is proportional to the number of upstream neighbors, that means the rate at which you attach to the node by redirection is proportional to its degree. Attachment rate proportional to degree is what's called linear preferential attachment. And so this is what, I don't know why the A here is black. Anyway, so this was what was publicized and popularized by Bard, Foss, and Albert in 1998. But it's amazing, in fact, that this is also known as the Yule process from 1925. And Herbert Simon in 1955 solved the model completely. And so all the results that were in the Bard, Foss, and Albert paper were actually done by Simon in 1955. I don't know if any of you know who Herbert Simon is, but he's an economist. And he had this propensity for always being 40 years ahead of his time. So he did seminal work in many different fields of economics. And it was only in his later years that people realized, no, he's not a crackpot. Yes, in fact, he's 40 years ahead of his time. So later in life, he won a Nobel Prize for economics. The one other thing, though, as you're going to see, is that this model gives me linear preferential attachment with a little shift. And if you don't know what you mean by shift here, it'll become clear in just a moment. Okay. So in order to demonstrate that this redirection mechanism gives rise to linear preferential attachment, let's now write down the master equation for this process. So there's a little cartoon to help us understand what's going on. So what I have right now is the master equation for the non-redirection part. So for the probability 1 minus r, I just attach to a random neighbor. So I take the master equation for random recursive tree, which is everything here, which we had before, and I just multiply by 1 minus r, because that's a probability I'm actually going to do this event. But with the probability r, I attach to the ancestor of the node. So there's an r sitting out in front. And now what are the terms that are here? So for example, let's just focus attention on this term. The point is that with the probability proportion to the number of upstream neighbors. So a node of degree k has k minus 1 upstream neighbors, 1 downstream neighbor to make total degree k. But it has k minus 1 upstream neighbors. And if I attach to a node of degree k by this process, then I'll kill the number of nodes of degree k because I've created a node of degree k plus 1. So this is the rate at which I lose nodes of degree k by the redirection process. This is the rate at which I gain nodes of degree k by the redirection process. And now you just do a little bit of rearrangement. It's just simple algebra to put everything together. And what you see is that the thing which is multiplying n sub k is linear in k.
Do you really get an extra delta function?
You really get an extra delta function. I see. So what should happen here is, I don't have 2 delta functions. You're right. So that's the screw up. I mean, there's only 1 delta function. So cross this out.
1 minus r plus r.
Right. Exactly.
Bracket.
Okay. Anyway, so if we gather these terms together, one sees that the thing which is multiplying nk, which in random recursive tree was just 1, now has a k dependence. And so that's what I mean by shifted linear attachment. So let me rewrite this in a little bit shorthand notation. I'll write it in a suggestive way. A sub k is the attachment rate to the node of degree k. A sub k minus 1 is the attachment rate to the node of degree k minus 1. And in this formula, A sub k is exactly equal to k plus this shift. And the denominator is just the sum of all possible rates of anything happening. And again, it's just trivial algebra. You'll find that it's just equal to n divided by r. So by this mechanism, we have recast the random recursive tree into linear preferential attachment.
albeit with a little shift. And we'll see what the role of the shift is in just a moment. Because it might seem like, who cares about this little small factor, but it turns out to be actually quite fundamental. Okay. What?
Is this the same A, which is a different subscript? Because it doesn't look like it.
Which one are we talking about?
Well, is AK minus 1 and AK still the same thing?
Yeah, same thing. AK is K plus 1 over R plus. Oh.
That's
Oh, I see. Yeah, let's
one.
There's a plus missing in the other.
Yeah, something. There's some stupid algebra mistake.
So it's only on the same A.
Yeah, this is certainly correct here. Okay, so I'll fix this. Okay, so what I want to now present to you is the solution to the master equation approach for this linear preferential attachment model. And in fact, we can do better than that. We can not focus just on linear preferential attachment. We can focus on any kind of preferential attachment. So the work I'm going to present to you now is work I do with Paul Kukuski and Francois Legras, and also more or less simultaneously with us, there's a group in Portugal, Dorgosta and Mendes, who also applied the same kind of technology to solve the network. So again, our master equation, which I hope is starting to look a little bit familiar now, since I've been beating it over the head for a week. Yes, question.
So the reference that you mentioned, Simon, what was it?
Simon.
I know the Ewing word, but Simon.
Pardon me?
I know the Ewing word, but
Right.
Simon was the first name?
Herbert Simon. It's in Biometrica in 1955. And good luck in finding the journal for free. I don't know. I have the actual paper copies. So I must have gone to the library and photocopied or something. Wow. Yeah, I
Well, nowadays you can ask for in the library now, it will come with a PDF, so you can
Okay. You young whippersnappers. Okay. Anyway, so here is our master equation, and again, the rate at which you attach the node degree k minus 1. Let's leave it now perfectly general. Let's just call it some arbitrary function of k. So the rate at which you attach the node degree k minus 1 is a k minus 1. The rate at which you attach the node degree k is a sub k. And I divide by the total rate, so this ratio, ak minus 1 over a, is a probability in a network of n nodes that I will attach to a node degree k minus 1. And similarly, this factor is the probability that I attach to a node degree k, and then the delta function for creating a node degree 1. And let's now consider fairly general types of growth rates. I'll consider power law preferential attachment, where this gamma will be any number complete. So one thing that turns out to be important in this, and if you remember from my first lecture about aggregation kinetics, if you are stuck with a formidable, or if you're faced with a formidable set of master equations, it might behoove you to first look at some low-order moments of the distribution to get an idea of what to expect. So if we look at the total rate, by construction, that's the sum, the rate of attachment node degree j times the number of nodes of degree j summed over all nodes. And if a sub j is j to the power gamma, this is nothing more than the gamma moment of the degree distribution. So I'll call that thing m sub gamma. Now, if I look at the equations for the moments, they are actually quite simple. For the zeroth moment of the degree distribution, so j to the 0 nj. So what is sum nj? That's just the total number of nodes. And every time I add a new node to the network, the number increases by 1. So the time derivative is equal to 1. And notice here what I mean by time derivative is actually dm0 by d capital N. My only variable is n. Similarly, for the first moment, that's equal to the sum jnj. But what is jnj? So j is the degree of a given node. N sub j is the number of nodes of degree j. I sum up over all nodes in the network, and so I'm just counting the number of stubs around every single node, which counts the number of links twice, because I count this link from this node, but I also count it from that node. So in fact, this thing is growing by 2 every time I add a new node to the network. So we see that the zeroth moment and the first moments, their growth rates are constant. And so we know that these things will grow linearly with n. And so what that suggests is that this total rate of anything happening, which was the gamma moment of the distribution, should also grow linearly with n if gamma is between 0 and between 1. So this range of either no preferential attachment up to linear preferential attachment
ought to be somehow in a similar universality class, and we'll see that it is, and the total rate is growing linearly with n with some amplitude which depends on this preferential attachment exponent again. So we now make the ansatz that the total rate is linear in n. Let's also make the ansatz, we've already seen for the random recursive tree, that the degree distribution is equal to the total number of nodes times the fraction of nodes of degree n. So if you just take that ansatz and plug this into the master equations, it will convert this differential equation into a simple recursion formula. And again, this is high school algebra to solve this because it's just a simple first-order recursion formula. And if you do that recursion, here is the formal solution. So that's it. That's the full solution for the degree distribution of these preferential attachment networks in the limits of n going to infinity. So in fact, I've swept something a little bit under the rug, but this is all based on the assumption of n very large. And if n is finite, one has corrections vanish like 1 with the square root of n and higher powers of n. But that's irrelevant to large n numbers. Okay. Now, the one thing about this exact solution is that even though it's very compact and kind of looks pretty visually, it's completely opaque because, like, what's contained in it. So we have to look at the asymptotics of this distribution. So now comes a little bit of pain, but it's like very straightforward pain, which is we have to figure out, first of all, what is this mu, which was the amplitude in the total rate, and to determine the total, this mu, which is like a parameter inside of this exact solution, if I sum ak, nk, this is the total rate, but since I'm looking at little n, it's a total rate divided by n, which is what we defined as n. So we can get a self-consistent equation for mu by just summing this thing over all degrees. And the thing is that this equation you can only solve numerically, and if you solve it numerically, you find that this rate, or this amplitude, is smoothly going between 1 and 2, as the attachment rate exponent goes between 0 and 1. And you can solve for it perturbatively at this end and that end. And if you want to do this as an exercise to work out these perturbative expansions, you're welcome to do it. But it doesn't tell you anything much in terms of understanding. It just gives you like how to get the actual numbers out. But now let's take this as a given that this amplitude mu is just some smoothly varying number, and then investigate the asymptotics of the distribution itself. So again, we start with a formal solution. And I want to now look at the asymptotic behavior of this distribution for this power law preferential attachment. So what I'm going to do to find the asymptotics is this is a very handy-dandy trick, which if you haven't used it yet, it's worth learning because it's very handy. So you see here we have a product of 1 plus a small correction factor, which is going to vanish as j goes to infinity. So if we have this product, 1 plus epsilon j to the minus 1, what you do is that you write this as e to the sum of the log of this thing. And if this thing is going to 0, then e to the sum of log. Maybe I should write this down because it's like a lot of words. So you have something like the product 1 plus epsilon j to the minus 1. So I'll write this as e to the logarithm of 1 plus epsilon j. Well, now I put it over here. E. And the product will be this, which I'll then write as the product equal e to the minus summation epsilon. And then I write this as e to the minus integral epsilon. So this is epsilon j, epsilon j, is something like that. So if you haven't used this little trick, learn it because it's so handy for these sorts of things. So I'm just using that, and given the fact that I know what Hj is, it's just a power law, with very simple, straightforward algebra, you will find that for gamma between anything above 0, 0 and above, and less than 1, one gets a stretched exponential decay. The asymptotic part of this distribution that's interesting is e to the minus k to the 1 minus gamma power. So a fractional exponential. So this stretched exponential behavior is what might be called the universal behavior of this model, because you get robust behavior, the same type of exponential decay, for every value of gamma between 0 and 1. So this is what I call universal or generic behavior of this model. On the other hand, if I have gamma larger than 2, one gets what might be called the Bible phase. And what I mean by the Bible phase is this. If the attachment rate is so much biased towards a high degree node, you can have the following situation. That here is a Bible, and all of us in this room, because the Bible is so famous and so popular, we all cite the Bible. So the next paper I write, I cite the Bible. The next paper Christina writes, she cites the Bible. Yuli cites the Bible, we all cite the Bible, and we can ask, what is the probability that this pattern of behavior continues forever? So here's what we want to do. We want to have the last paper, the last person in the room, the last person who walked in, who's walking in late. You also cite the Bible. And how does that happen? So if I have a total of n plus 1 total nodes, then I have one Bible and n subsidiary nodes. Then I attach the new node to the Bible with the following probability. I attach to the Bible the probability equal to the degree of the Bible, which is n. And if the attachment rate is n to the attachment rate is proportional to the gamma power of the degree, so I attach to the Bible the probability n to the power gamma, and I have to divide by the total rate of attaching to anything. So this is the probability that at this stage of the process, this last paper attaches to the Bible. And so the probability that the Bible lasts forever is that I just have to take the product of these attachment probabilities from 1 to infinity. And the thing about this, if you use this little trick over here that I showed you, you can immediately verify that this probability of creating a Bible is 0 for gamma less than or equal to 2 and non-zero for gamma larger than 2. So we find the Bible phase. Let me not talk anything about this model because this is really kind of a detail. What happens here is that one gets a Bible-like situation where one node has almost all the links in the network and other nodes have a few citations. Maybe somebody will cite me because I'm, a minor player in the game, but most people still cite the Bible. And the way that this happens is actually very mathematically intricate, but not of perhaps physical interest. So now let's come to the meat of the problem, which is what happens when we have strictly linear preferential attachment. And the thing about this, which is really quite amazing, is that in this particular case, and only in this case, we get power law behavior. And the degree distribution exponent, which Barbasi-Albert first found to be k to the minus 3, and which got a lot of attention, it turns out if you look at this more carefully, the exponent of the degree distribution can take on any value which is larger than 2. And for those of you who have been imbued with some of the dogma of critical phenomena, this is actually a very disturbing state of affairs because, if you sort of say the standard buzzwords, you have scale-free network, you have things happening on all scales, and in the end you get like a collective phenomenon where there's no natural scale. This is where universality should hold, where short-range details of the model shouldn't matter, and so one should have universal exponents. So in the case of the scale-free network, linear preferential attachment is lying on the edge of disaster because on this side you get stretched exponential decay. On this side, you get the analog of a gelation phenomenon that one node takes over. And right on the edge, one has power law, but the power law is non-universal. So now let me turn to what is the origin of this non-universal degree distribution. And so, roughly speaking, the mechanism is, again, buried in this little mathematical trick that I showed you, that if you write down for linear preferential attachment, and just write it as the product of this product is a sum, e to the sum of something, and then expand for small correction factors. If the attachment rate is linear, the crucial thing is that up here in the exponent one has the amplitude, mu, ultimately translates into the exponent itself. So the point here is that this number mu, which was essentially the normalized total rate of anything happening, ultimately transforms into the exponent. So an amplitude that appears in the overall reaction rate ultimately affects the exponent. So the point here is that, as I showed maybe 3 slides ago, this amplitude mu for strictly power law preferential attachment range between 1 and 2. In general, for a linear preferential attachment, or what I would call asymptotically linear preferential attachment. So what I mean by asymptotically linear is the attachment rate is some number times k plus corrections. And depending on what those corrections are, this amplitude can take on any value between 1 and infinity, giving rise to an exponent between 2 and infinity. Let me show you 2 examples where you can solve everything explicitly, and then there's no ambiguity about what can actually happen. So one example is what might be called strictly linear preferential attachment, AK exactly equal to K. In that case, if you take that little product formula I showed you a couple of slides ago and just plug in AK equals K, you very quickly find this distribution. And so it's 1 over K cubed asymptotically, but in fact we have a bit more because we have the amplitude and we have everything. The other example is shifted linear preferential attachment. So again, if you plug this K plus lambda into the exact formula for the degree distribution, and then do a little bit of gymnastics. So here is the exact answer. You plug this in, and a little bit of gymnastics is how you relate products of factors to ratios of gamma functions. And it's just kind of one of those things that, you know, if you're not familiar with it, seems black magic, but once you've learned the trick, you'll never go back to doing it any other way because it's just so much easier. And kind of it's like, it's almost you can recognize right away that the answer has to be this. Anyways, with that little preamble, the point is that the asymptotic decay of this distribution is just related to the values of the amplitude sitting here, these correction factors, it's asymptotic at k to the minus 3 plus lambda. So since the shift in the linear preferential attachment, physically the shift can be anywhere between -1 to infinity. Because if it's more than -1, then the network can't start growing. Because if I have a node of degree 1 and the rate of attachment is k minus 1, I'll have 1 minus 1 equals 0. So I can't have the shift being any smaller than -1. And so that restricts the range over which this degree distribution exponent varies. But I want to emphasize here something that's really quite striking, which is, let's consider shifted linear attachment k plus 1. So if the degree is 1 million, who cares whether the attachment rate is 1,000,000 or 1,000,000 plus 1? That shouldn't make any difference at all, right? Doesn't it seem reasonable? And yet, one gets, if I put a tiny little shift here, a dinky shift of 1, once I get to like size, degree 1,000,000, this actually shifts the exponent by 1. So this is kind of an amazing feature, and it's something you might want to think about, like what is it that gives rise to a shift in the exponent by changing a little dinky constant by 1, especially when you're talking about large degrees. And if someone wants to know the answer, I can tell you after I let you sweat about it for a bit. Yes?
The crossover doesn't return to one shape, is that right?
What do you mean by crossover?
Well, presumably for a small k, it doesn't go like k to the power.
Yes, it does. Yes, I mean, it goes, very quickly. Like,
It's not wiggle?
pardon me?
You mean it's not wiggle, it's equal to? No.
No, what I would say here is that the degree distribution, this power law behavior goes over a range that starts at 1 and goes out to like, k to the, there's a k max, a natural sort of upper cutoff here, which depends on the degree distribution exponent. Let's say for linear preferential attachment, that cutoff value is n to the 1/2. So between degree equal 1 and degree equal n to the 1/2, you get almost perfect power law behavior, modulo like tiny little corrections that are become invisible when the network becomes large. So there's no crossover. Yes?
What if you set the rate AK equals K for K less than 1,000,000,
right,
and AK equals K plus 1?
That's truly an amazing thing. In fact, you can do even something dinkier, which is you can say A1 equals 2, and all the other AKs equals K. In fact, for that particular example, you can work everything out analytically, and you get an analytic formula for this degree distribution exponent, which changes as a function. So let's make A1 equals just arbitrary, A1, and AK equals K. Then you get an exponent which depends on A1, and you can make it vary anything you want between -2 and infinity. So it's quite remarkable. So these little dinky changes really make a big difference. So in the last few minutes of this talk, I just want to mention another aspect about the network, which I think is really kind of overlooked, and I think it's worth emphasizing because it provides new insight into the structure of these linear preferential attachment networks, and that is the genealogy of the network. So here is a network at some stage of its growth, and inside of this geometrical structure, there is an underlying genealogical tree in the sense that here is the parent node of the network. So let's call that the 0th generation. And then attached to the 0th generation are nodes 2, 4, and 6. So they comprise generation 1. And then I can build up generation by generation the network itself. So here again is the original network and the underlying genealogical tree, nodes 2, 4, 6, 8, 9. So 8 is attached to 1, 9 is attached to 1. So they comprise generation 1. And the remaining nodes comprise generation 2. And if we study the genealogical nature of this tree, we learn some new facts about the actual size of the network itself. So, again, here's just to emphasize, these are nodes of generation 1, and these are nodes of generation 2. So what I want to now study is what is the size of the G generation? How many nodes are in generation G? So let me call L sub G the number of nodes in generation G. And so this satisfies a very simple rate equation now, because how does the number of nodes in generation G change? In order to change the number of nodes in generation G, so G is 2. In order to add to the number of nodes in the second generation, the only way that can happen is I have to attach to a node in the previous generation. So the rate of change of the number of nodes in generation G is equal to the number of nodes in generation G minus 1 divided by the total number of nodes. So this genealogical picture that I've just presented to you is for random, or the random recursive tree. So I attach to any node with equal probability. And so the rate at which I attach to the nodes in this generation is equal to the number of nodes in this generation divided by the total number of nodes. So that's the rate equation. And it's a very simple exercise to solve this system of equations. Start with L1, and you solve for that in terms of L0, L2, and you just do it one by one. And you find a very simple form as a function of G, that it grows exponentially in G for small g, but this G factorial wins out in the end. So eventually this number of nodes in generation G grows with G quickly and then very quickly falls off. And where the number of nodes or in the G generation is 1, this defines where it's the very last generation. And again, this is very simple mathematics, so I'm not going to present any details here. The last generation, G max, is defined by this number, E log n, is when this L sub G goes back, starts at 1 and goes back down to 1. So what we learn from this is that is the depth of my tree. But the diameter of the tree, the maximum distance I have to go to join any 2 points, is the worst I could possibly do is start at generation G, go all the way up to the parent, and then go somewhere down here to meet some other distant family member down at generation G. So the point here is that the diameter of the network is twice the maximum depth, so it's 2d log n. So what we learned from this is that the diameter of the network is scaling logarithmically with n. And in fact, this is a very generic feature of these random networks, is that they're usually not very broad in size. I mean, even though you might have a billion nodes in the network, the radius is of the order of log of a billion, and so that's a number like of the order of 20. And that's part of the reason why it's so easy to get anywhere in the world now via the web, because there's enough random connections, and so it's easy to get almost anywhere very quickly. Now, the last thing I want to mention about this is what happens now for linear preferential attachment. So if I really have linear preferential attachment, then this genealogical tree thing doesn't seem to be very easy to deal with, because the rate at which I attach to a given node depends on its degree. And this is where this redirection trick turns out to be incredibly useful, because we've seen that we can generate linear preferential attachment by redirection. So if I use redirection on the genealogical tree, we can again write down a simple rate equation for the size of the G generation. And so here is a cartoon of how this works. So first of all, how does the number of nodes in generation G change? I can first of all attach to a node in generation G minus 1. And that happens with the rate or probability, the number of nodes in generation G minus 1 divided by the total number of nodes. But if I'm going to use the redirection trick, I say with probability 1 minus r, I attach to a random target. But with probability r, I will attach to a node, and then I go to its ancestor with probability r. And so the number of nodes that happen to lie in this generation 2, I can either have attached to a node in generation G minus 1, or I attach to a node in the generation itself, and then by redirection, went one layer down, and then both of these processes contribute to the gain in the number of nodes in generation G. And for the case where AK is exactly equal to K, I didn't emphasize this point, but now let me emphasize it, because I should have said it like 5 or 6 slides ago, that you saw from that redirection model that the shift was actually involves the redirection probability. And when the redirection probability is exactly equal to 1/2, the shift goes away, because the shift was between -1 to +infinity. And so when the redirection probability is 1/2, the shift goes away, and we get exactly linear preferential attachment. So we have an equation which involves dLg by dn is 1/2 lg minus 1 plus 1/2 lg. And what I would say here is that this equation is morally similar to the equation when r is equal to 0. You can't solve this one exactly in all detail, but one can look at it asymptotically and get the same character of the solution, which is that the largest degree is of the order of log n itself. So one sees that both for the random recursive tree and for linear preferential attachment, one has a logarithmic growth in the diameter of the network. Okay, I guess I'm pretty much at the end here. So I hope I've given you a sense that the master equation is a very nice tool, it's a very simple tool, and it's a very well-directed tool for the problems at hand. And that for the case of these complex networks, that one can understand many details, essentially all details of the degree distribution, and other topological features of the distribution in a very, I would say, very pleasant way. I mean, a lot of these calculations when we were doing them for the first time, when you first write this stuff down, it's like very mysterious, but it's like everything sort of, it seems like you have a very powerful flashlight, and you're looking down the cave, and like you can see down to the next bend, and you get there, and then you can turn the flashlight, and it leads you always in the right direction. So we found this to be just a very pleasant line of work when we originally did it. And so let me now mention some open questions. One of them you already saw at the public lecture, which is that why does linear preferential attachment appear in so many places? And one of them was the case of the attachment rate in the physical recitation network. So this is essentially the same data I presented to you last night, or 2 nights ago. The only thing here is that the black is the attachment rate in the year 2000 to all papers in the physical review data set from 1893 up to 1999. And then I did smaller slices just to see, like, was there some change as a function of time? And in fact, there's no real change. So one sees that for the citation network, that there seems to be linear preferential attachment seems to be a very good approximation. Other things that might be interesting to think about is that we have not, in all of this theory, said anything about spatial structure. And if one is really worried about, say, the internet, which is like, routers and wires and all those sorts of things, and there's costs associated with making wires, then one might have to deal with spatial structure. And indeed, the computer scientists have been worrying a lot about models where the spatial structure or the cost of a link is part of the model itself. And this is an area for which I think there's still a lot of room for interesting modeling yet to be done. And another thing is that this is all for like a static network where the notion of a link is something that you might think of a good thing. But in social networks, links are being rewired. Some links might be considered good because you might be friends with somebody, but some links might be in some sense bad. You have some enemies, and how do you navigate a social network where there's some friendly relationships, unfriendly relationships? There's also large-scale organization that one has to have communities as well. So I think that for these sorts of realistic social settings, the field of network analysis, the formulation of models, and the methods of solutions are still pretty open. So with that, I'm done.
So this sort of analysis screams to be taken to things like Facebook, Twitter, etc. Has that been done? Who's doing it? What's the status? What have we learned?
Can you say this?
So he said that this kind of analysis screams to be taken to Facebook, Twitter, all those sorts of social networking sites. So what I would say is that there are people who are using quantitative tools to analyze this. There's a group at HP Labs. There was a guy named Bernardo Huberman, maybe you've heard the guy's name. And there was Lada Adamich, who now has moved to the University of Michigan. And there's also Duncan Watts, who went from Columbia University to Yahoo. And so there's sort of a collection of people who have, Duncan Watts was trained as an applied mathematician, but he was a sociologist. So I think that these tools are now starting to get applied. I have to admit, I don't know what real lessons we've learned yet, but I'm kind of ignorant of the kinds of questions that these people ask. The thing about the sociologists that sometimes they ask questions that we as physicists don't care about, and that we as physicists, we ask questions that sociologists don't care about. So I think we're still grappling like, what are the important questions, what are the basic issues? Certainly you can say, how many friends does the average person have? And so those sorts of characterizations that anybody could care about. But then there's other things where, like say problems involving social segregation or different economic classes, different stratifications. There's details at the social level that maybe a physicist couldn't care less about, or that it then screws up a model somehow. And vice versa. Our naive modeling, the sociologists sometimes look at us and say, you didn't account for the fact that there is an age spread in your population. So I think that we're still at the level of feeling each other out and trying to find the right common language, and we're not there yet. But I think it's really quite open. Yes, Bianca.
When I come back to these questions with the number of friends, the average number of friends. So my friends have more friends than I have.
Right.
But then their friends have more friends than me. So there has to be a convergence.
Well, so I would say at this stage there's something not very well understood, because yes, if your friends on average have more friends than you do, and yes, then you go to the grandfather level. And so, in fact, I spend some time trying to understand, like, suppose instead of you redirect to your father, you redirect to your grandfather. You could not figure out what was the dynamics of that world. And then other people looked at things where you redirect anywhere along the chain of the genealogical tree all the way to the origin. And some things, there's some weird features about it that just aren't very well understood. There's actually a very recent paper by Edna and Krupski, who have actually looked at that kind of a model and only found one thing, which is that if you imagine that you attach anywhere along the genealogical tree uniformly along it, then you can actually derive some results about the degrees of the first few nodes. But I would say that this is really not understood. And it's quite. I have to admit, I did spend some serious time trying to understand it, and I was frustrated. So take a crack at it. Yes, Royce.
The question about this linear differential action. So if AK take the time that the coefficient of K becomes 1, what happens?
Well, the thing is that the coefficient really doesn't matter, because if you go back to the original master equations, there's like an nk dot, and then there's AK, nk in the numerator, and then a capital A on the denominator. So an overall prefactor cancels out. So it doesn't matter.
Affects lambda.
Yeah, so what I would say is that if you're going to say that AK is equal to AK plus lambda, I would say just divide through by little a and write. Yeah, so lambda changes the shift. That's right. But so the overall factor there's an overall factor that's indeterminate. Yeah. Right.
But that relates to the other question I was going to ask, is that when you say that the exponent is quote non-universal, and the usual Archie language is where you have a fixed model.
Right.
So now the question that I would ask is, in one case the universality is fast with this fixed model. Who goes in this? What are the things I can change and still get to this particular exponent of mu to the 2.65?
Yeah, well, so I guess what I would say is that as long as k goes to infinity, a sub k is linear in k. All sort of growth rates that have that property will go to this fixed line.
So therefore, like k to 1/2 is putting there, that will make it different.
So if I had like ak is equal to k plus k to the 1/2,
That is
okay. But if the leading behavior is not linear k, then you fall off that fixed line. Yes.
This is about the genealogical tree for the linear differential attachment.
Yes.
So I think I need to look at the equations.
Okay.
Was this guy here? Yeah. So, for example, in the L, there could be leaks in a generation, right? Like things that end at that generation. There could be what? Leaves, like the ending node, which don't propagate.
Yeah, so like for example here, these are like the sort of top end, that's the top of the tree somehow, or actually it's the bottom of the tree.
Yeah.
Okay.
So do they deserve to get the same arc? Like, because they don't have the same number of upstream neighbors as something that is propagating, right?
So you're asking, what is the rate at which that these nodes, I can't ever reach them by attaching... no, I think this is...
So when you say R for all nodes in generation 1, if you say it's an R.
I see. So what you're saying is that for the last generation, Yeah, I see what you're saying. So your point is that for the last generation, if I attach to this, I can only attach to the nodes in this generation directly. Like if redirection will force me down here. So there's some funny business about the very last.
Something like that.
Yeah. What do I say about that? No, I think this is true forever, because again, just look at this example, which is, let's look at DL2 by DN. How does that change? I can either attach, because the thing is that what you mean by it being in generation 2 is that you're relying on this line. So the way you can do it is you either attach to generation 1, or you attach to the last generation and then redirect. And so this equation is true for all generations. There's nothing funny about the last one. So I see that this is actually true in general. I mean, you have to maybe stare at it for a minute, but I'm confident it's correct. Yes, please.
This may be something obvious, but for the linear preferred graph, the k plus lambda can only go as low as -1 because you want to have this graph evolve.
Right.
What happens if you have the initial graph, instead of 1 node, you just throw in a random graph, say 2 nodes?
Okay.
How would this affect the overall evolution?
Well, okay. What I can tell you with perfect confidence is that the asymptotic behavior will not change. What does change are, again, in making the ansatz, if capital NK was capital N times little nk, there's actually corrections which are lower order n. And the correction terms lower order n will be affected by the initial conditions, but it does not affect the asymptotic behavior. And in fact, we actually worked out in complete, gory, horrible detail the difference between starting with a dimer initial condition and a trimer initial condition. And it's a horrible calculation, and all the details you can look at. It's a paper in Jake Dizay in 2002. And in fact, in today's condensed matter archive, there's a paper by Godresh and Jean-Marie Luc who have taken what we did there, and we took a sledgehammer, they took like an atom bomb, and they just killed the problem. So they have every possible detail under the sun about like finite size effects. It's quite an impressive paper, actually. Yes.
So this might be my lack of experience with this topic, but every time you got a formula, you took k to be large. I looked at the details. Is there any particular reason or physically significant for doing that? Instead of worried about is k small important at all?
Well, I guess it depends a lot on what you're looking for. I mean, part of the reason why this whole scale-free game became important was the fact that instead of having very narrow degree distribution, one had a broad tail. So the interest was actually looking at the large degree tail, because initially it was a surprise that you would get, based on, say, what you know from the Erdo-Schrödinger random graph, where one gets a sharp degree distribution. Once you've got the game that the degree distributions were non-sharp, it was the nature of the tail that was of interest. So, no, people generally don't look at the small degree tail. That's good.
What's the behavior of A of k goes like k log k?
If it goes like k log k, then it turns out that the degree distribution, I think, is like, if I remember correctly, is something like it was like k to the minus 3 times log k. I mean, if you put in a logarithm correction, you get a logarithm correction of the degree distribution itself. I actually worked this out a long time ago, and I forget what happens, but it can be done. And so logarithm correction in the attachment rate gives rise to logarithm correction in the power law.
Well, there are no more questions. Oh, one more.
So for, you were saying that if someone asked you to explain what was going on, but adding 1 to a million and getting like an actual difference in the exponent.
Right.
So I'm asking.
Do you guys want to sweat the question, or shall I answer it now? You tell me what to do. I'll answer it if you want me to answer it. So the question is, like, what is sort of the underlying reason why changing k, the attachment rate from k to k plus 1, why that makes a shift in the exponent? Please answer. Okay. I'll give you a partial answer for it, which is that if you actually look at, if you just focus attention on a particular node, what is the sort of attachment rate on a particular node? So it's going to depend on its degrees throughout its entire history. And what you'll see is that the attachment rate to a particular node is actually governed by a multiplicative process, because the rate of attachment to a node that has degree 3 will be like
3, but then if it changes to 4, there'll be a product of 3s and 4s divided by an overall denominator, which is the same for all nodes. So what you see is that the attachment rate is an underlying multiplicative process. And so that is why the model is very unstable to these tiny perturbations, because when you have a multiplicative process, then little tiny tweaks on the multiplicative process play a huge role in the average of the distribution. So that's sort of 3/4 of the answer, but then you can work out the details.
I guess with that, we thank Sid again.